Hello everyone, it's Jay, and today we'll be talking about the cathode ray experiment. So in our last video, Angela taught us about the Millikan oil drop experiment, which allowed us to determine Q, or charge of the electron. But we still don't know mass of the electron, and that's exactly what the cathode ray experiment helps us to determine. So let's walk through some of the fundamentals of the setup of the cathode ray experiment. So we take two plates exactly like this, and we want to create a magnetic field between them. So one of them will be North Pole, and the other one will be a South Pole. And it's important to note that the North Pole plate is in front of the South Pole plate in this diagram. So magnetic fields run from north to south. So our magnetic field moves something like this, and we can assign a strength to that magnetic field, B. Now, let's say that we have a charge, and for our sake, we'll say that the charge is positive, and now it moves horizontally through that magnetic field at velocity v. Well, that charge will have a force that acts on it by that magnetic field called the magnetic force, or F magnetic. And its magnitude, when the velocity and magnetic field are perpendicular, as they are here, is equal to the charge times the charge's velocity times the strength of the magnetic field. So we have the magnitude of our magnetic force, but we also know that forces have direction and magnitude. So how do we find its direction? Well, for a positive charge, we are going to use the right-hand rule. So that's true for positive charges. And for a negative charge, we're going to use the left-hand rule. And apart from the hand that we use, they work exactly the same. So we take our right hand for our positive charge drawn. We're going to fashion it somewhat like this. And in this, the index finger represents the direction of velocity. The cluster of the middle ring and pinky fingers represent the direction of the magnetic field. And our thumb is the direction of the force. So let's orient our hand in the direction of the velocity and the magnetic field. So our velocity moves from left to right, and our magnetic field goes from front to back. So we know that our magnetic force is upwards. So we now know the direction of our magnetic force. And because we have a force that acts on this charge, it actually doesn't stay in this straight horizontal line that we see drawn here. In fact, the charge will enter horizontally, and it will be deflected upwards ever so slightly because of that magnetic force, and that is known as deflection, which is abbreviated DEFL. And deflection is the key to understanding why the cathode ray experiment allows us to find the mass of an electron. All right, so I've redrawn our magnetic plates, our equation for F magnetic, as well as our right and left hand rules. And so now let's dive into some of the specifics of the cathode ray experiment. So it was first carried out by physicist J.J. Thomson. And the way it works is between our magnetic plates, we are going to place a long capsule, and we're going to suck all of the air out of this so in order to make it a vacuum. Now we'll place plates at both ends of our tube, and we're going to connect this via some wires to a battery. So this short line, long line is a shorthand for battery, where the short line is the negative terminal and the long line is the positive terminal. So setting up this circuit gives us an accumulation of negative charge via electrons on the left side and positive charge on the right side. Now, as that current increases, some of these electrons are going to pop off of that left side to the right side in a beam. So these are electrons. They travel in a beam called a cathode ray. So a cathode ray is just a beam of electrons. And the electrons will be traveling at some velocity v. So We have our north pole plate and our south pole plate. We know that we're going to have a magnetic field that runs between them. And this magnetic field has strength B. We see that the magnetic field is perpendicular to our velocity, and this looks very similar to our previous example. We know that there has to be an F magnetic, so let's find its direction. We know the electron's negatively charged, so we take our left hand, we use the left-hand rule, and we know that the electrons travel from left to right, and we know that the magnetic field goes into the page. So with this setup, our force is downwards. So our F magnetic is going to be downwards. And now, because we have that F magnetic, our electrons, like our previous example, do not stay in this straight line. They start straight, and then they are deflected downwards. And so we have a deflection. So how does this deflection allow us to find mass? Well, we know that deflection is the amount that these electrons move. So it's proportional to acceleration. And now from Newton's second law, which is that force equals mass times acceleration, we know another way we can write acceleration is force over mass. So the actual object that's deflecting is an electron, and the force causing that deflection is the magnetic force. But we can write magnetic force more specifically as that equation. So let's erase our F and let's replace it with our magnetic force equation. Q times V times the strength of our magnetic field. So now we can solve for the mass of the electron by going through what's known and what's not known. So physicists can measure this deflection, so they can know deflection. And recall that the Millikan oil drop experiment told us the charge of the electron. Physicists set their magnetic fields, so B is also known, leaving velocity and mass, which is the quantity we're looking for. Now, the way Thomson figured out velocity, as well as the proportionality constant involved, is by setting up a weaker electric field as well as the magnetic field. We've ignored that in our diagram, and the only important thing really to know for our purposes is that the velocity then was known. And so out of our 5 variables, we were able to know 4 of them. So we were able to determine that the mass of an electron is equal to 9.11 times 10 to the negative 31 kilograms. So through the cathode ray experiment, the mass of an electron could be determined. Thank you so much for watching.